Welcome to Natural Habitat Adventures Daily Dose of Nature. Today's presentation, The Aurora Borealis Through the Ages, Part 2, is brought to you by NatHab Expedition Leader Kristina Disney. Kristina earned a double major in biology and physical geography from McGill University and has published research on nitrogen fixation of sphagnum moss, in the
Oh, you
Journal
got it
of
right.
Botany. I had to take a second, though. She conducted extensive remote field work from studying marine mammals in New Brunswick to carbon dioxide and methane emissions research in the subarctic and biodiversity monitoring in northern Alberta. Kristina now divides her time between soil sampling in Labrador and the Yukon during summers, guiding polar bear tours in Churchill each fall, and working towards her PhD when at home. Kristina, we're excited to have you here today. Thanks for being here. It's your show.
Thank
Take it
you.
away.
Thank you so much, Rob. And thank you for taking a crack at sphagnum. I should change that just to say moss to give you a break, hey?
That's all right. I got to work on my pronunciation skills.
Oh, good. Hello, everyone. Happy holidays. As Rob said, my name is Kristina. I am very excited to squeeze this in between Christmas and New Year's. And these days, I don't study moss so much anymore. It's sort of interesting hearing your own introduction and you kind of remember all the things. You're like, oh, yeah, I did do that. So these days, I study water and I work in the subarctic with NatHab. And so it's kind of how I've kept my foot in the door up north. And I'm really grateful for that. As much as I love where I live here on Vancouver Island, the sun actually just came out. I don't know if you guys noticed that while Rob was doing the intro. It got a little glowy in here, which was quite nice. I do love Vancouver Island. I love the community and where I work now, but pretty much I always have some part of my mind is up north. And so guiding takes me back there. These webinars take me back there. And I'm hoping that that's kind of what I can do with you today is take you sort of back through history and how we think about the aurora, but also to kind of connect it to sort of chasing that north. We go north because we're trying to get to this time and space, this frame of mind, I think, is really what we chase. And that's why you'll find a lot of people who chase the northern lights. They've gone to see them all around the world. They'll travel to Scandinavia, to Svalbard. If you're going to do it here in Canada, Churchill, we're in kind of a 3 out of 4 nights. You got some of the best odds you're going to get. You can go to the Yukon, you can go to Alaska. There's different places all around the world. And so it's chasing wonder, right? It's a really exciting thing to do. And so for anyone who did tune in for part 1, the sort of what we were looking at or what we were chasing that time was the stories and the myths. And, they're foundational to so many different cultures. And in part 2 today, we're going to chase down some of the science, or at least some of the history of the science. Because I kind of want to bring us along to an appreciation. I'm going to do the Shakespeare style, where I'm going to tell you the end at the beginning. I'm really hoping that by the time we're done with our 45 or 50 minutes here together, we can have an appreciation for that saying we use all the time, the shoulders of the giants that we stand, giant shoulders that I stand on. I'm messing up the saying now, but that's okay. You get the gist, right? There are so many people that come ahead of us to build what we know and how we know what we know that we often, don't even mean to be ungrateful. Because you just take it for granted that these things are out there. And so hopefully by the end of this, we can have some gratitude for all those who came before us, who spent countless hours in the whipping snow and the blizzards to teach us what we know now. But just quickly, a little recap for anyone who wasn't with us. In part 1, we did a lot of really fun things. If you weren't there for it, I encourage you to go back. But just kind of some fun highlights from part 1 was we tracked down the oldest written record that we have of Northern Lights. It's from the Bamboo Annals, which you can find. We're looking at really, almost 3,000 years ago, which is kind of wild and crazy. And they were written down as these 5 colored lights that appeared. And the reason why we're able to confirm this has to do with being able to track geomagnetic storms to different things that are left behind in nature, like tree rings, things like that. So we can pair up historic records with processes that have left behind. So we kind of looked at some of the different written records. We looked at different stories. There's lots of different iterations of this through Inuit culture that you can find all the way from sort of Greenland across to Alaska. Just one real brief that I'm going to bring up here is that often the Northern Lights are tied to those who have passed away before you. And so sometimes it's called the Land of Day. And what you're seeing when you see the Northern Lights is you're seeing people who have passed away, sometimes violently, kind of depends on which iteration of the story you're going from. Sometimes it's children, but they're playing a game, which is one of the favorite games of the Inuit. So they have a walrus skull and they have to kick the skull up in the air, and then the skull lands, and whoever gets it to land in the teeth, you gets points for your team. It's not a game you'd find us playing very often anymore. Not a lot of us. We've got soccer balls, not walrus skulls. Right. So there's this tie, you know, sort of that tie to the afterlife. And they say that the sounds that people sometimes hear with the Northern Lights are the sounds of them playing. You can hear them running across the snow in the sky. And another thing I think to think about is that not everyone has the same stories, right? Lots of different cultures experience them to different rates, to different degrees. So this is a drawing from the Sami people. And so for them, like, you know, they talk about not wanting to make any sound themselves. There's actually quite a bit of fear in a lot of the old stories of the Northern Lights that are very much to be respected. And so you weren't supposed to make any sound. So if the Northern Lights were out, there's actually in this picture, it's sort of a bit of a throw in the face. But if you look, you can see that the reindeer is wearing a bell. So culturally, if the lights were to ever come out, they would take all of the sounds off of their reindeer. Women would cover their heads just so that you wouldn't draw attention to the lights. So different traditions there. Just another kind of fun one. There's way more. We covered a lot in the first one, so feel free to circle back. I just pulled out a few to kind of carry us over into this one. What I always like, because I grew up really loving Norse mythology, so for them, in Norse culture, the Northern Lights, when you saw those coming down from the sky, that was the reflection off of the armor of the Valkyrie. The Valkyrie were kind of they were the choosers of the slain. They were associated with Freya. They were sent by Odin to essentially decide who would die in battle, right? So they could either frighten you into weakness or encourage you and give you strength, right? And so you always hope that the Valkyrie were on your side. And so the Northern Lights could be a gift or a bad omen, depending on which side of the battle you were on. And these are stories from long ago, but I like to bring up this newspaper article because that feeling of the unknown, that superstition, for lack of a better word in English, we can learn all sorts of things. We can define things as much science as you want, but at the end of the day, we're still human. And so this is from 1938, not nearly so long ago. And people thought that things were on fire. People thought that it was a bad omen that predicted. It was actually, you can look this one up. It was from January 25th, 1938. And it was thought to predict World War II. This was an omen that predicted World War II. And so there's an interesting trend that I kind of pulled out at the end of our webinar last time, which was that where you are in the world decides how your culture relates to the Northern Lights. So this is kind of a cool picture that you're looking at here. It's just giving you an example of how you view the lights, whether you're in Norway or whether you see them in Italy, right? So there's different color spectrums we can expect to see it through: purples, greens, all the ways into reds. And then it's showing you sort of correctly the height or the altitude you'd expect to see them at. And then with that, the colors you'd expect to see. It has to do with which gases are reacting. And so if you're from the south, just because the angle that you're actually viewing them at, you often only see red. And again, those can creep closer, but if you're from the north, you're looking sort of straight up at them, you can see a whole arc, or what we would call a corona. And then as you move south, you sort of see sheets, and then eventually it often turns into more of a haze. And then depending on the size of the storm, that range can extend further south and shift back and forth. So it's not static, it's always kind of moving. And so for cultures that always had them present, the narrative in their stories is different. They always, it's not an event, it's something that is ever persistent. So when you use the example of the afterlife for the Inuit, it's an ever-present companion, right? Death is always there, that transition from life to death. Whereas if you go further south and they see them much more sporadically, sometimes some people only see one or two in a lifetime if they're lucky. They become these predictors. They become these big events that, in this case, it was a Roman city that thought we're going to burn down, right? That's what they thought the Northern Lights were. And so it's your relationship to it depends on where you live, and then your culture builds, its narrative around them out of that. And so I'm going to use that as kind of our jumping off point, and we're going to switch now. We're going to switch now from culture into science. But even as I say that, I want to switch us over with a poem who was written by the poem, excuse me, was written by a really prominent Northern Lights scientist who was alive kind of circa, well, oh, he did that documentary in the 1972. So let's say actually he passed away in 2016. I know that. So there's kind of a range of when he was working, but he wrote this, and I think it does a good job of, of I mean, there's so many things written about the Northern Lights, but this one I think covers really a lot of how we feel and how we try and perceive it. Called Let the Spirits Play. What awesome sights are these northern lights, whatever be their meaning, as they dance and prance their ritual dance, shifting, fading, gleaming. They pulse and beat and never repeat, showing endless variation, on a theme or a dream that always seems some mystic revelation. Sibilant green with vibrant sheen, purples, reds, and yellows, muted shades that glow and fade, soft and rich and mellow. Changing shapes from curtain drapes to dragging, slowly creeping, curling tight, then bursting bright like goats so nimbly leaping. Flickering fires of funeral pyres of tortured souls departed. Spirits at play at the end of day, their nightly games just started. A row of lances now advances, armies struggling in the sky, their proud parading slowly fading, disappearing from the eye. What are these lights that fill the nights of Arctic cold and silence, with flames and games of unknown names and hints of heavenly violence? Do they foretell the funeral knell, sending monarchs to damnation, or imminent wars bringing death to scores and endless devastation? Is Mother Earth their giving birth from secret caverns distant, to eerie lights that break long nights, where the sun seems non-existent? For centuries now, men have wondered how this polar show is rendered, a reflected glow from Arctic snow, from a cosmic cloud. Oh, excuse me. Perhaps a reflected glow from Arctic snow or moonbeams caught suspended, perhaps the shroud of a cosmic cloud from far and unknown places, or the baleful glare from a comet's hair that swiftly onward races. Is it a rent through heaven's tent where fire and brimstone's burning, or a glimpse through the door of gods at war, lunging, twisting, turning? Now men must know, so men will go to the ends of earth to answer the question why the Arctic sky is reserved for the merry dancer. They fight the snow and winds that blow through cold and endless nights to reach that place where face to face they meet those northern lights. One day we'll look and we'll find a book where mathematically treated will be the story of nature's glory, examined, proved, completed. But I'll not regret or be upset if never see the day. I prefer to dance in ignorance and let the spirits play. So I love this because, I mean, he does such a good job of sort of bringing it to life and encapsulating it. But here is a scientist. Here's someone who has studied it his entire life, right? And at the end of the day, as much as your whole life's pursuit is about answering the mystery, sometimes it's just the mystery itself, that's worth being there for, right? There doesn't ever need to be an answer. So I'm going to say that, and I'm going to hold on to that thought, even as we dive into about maybe 150, 200 years of research, of science. We're going to do a little bit of history here, and I'm gonna start us off with the 1600s. Essentially, we're going to start us off in kind of the heart of the scientific revolution, and this is a turning point when we think about, I'll just say, Western science. It's kind of a boundary between sort of ancient um, ancient thought and modern science. So again, still relying really heavily on the Greeks and the Romans and things like that. But there's a shift to this more empiric way of thinking, and it's also this rapid collection of knowledge. There's all these different innovations, and this new kind of science emerges. So it's just, obsessed with data collection and observation, and not that it wasn't before, but it's just we've got more toys that we can tinker with. And so there's about 200 years where it's really centric to Europe, and then eventually by about the 19th century you see it expand across the globe. But it's kind of siloed for that period. And so this kind of kicks off, that scientific era kicks off with the Copernican revolution, Copernican revolution, where we have, all of a sudden, wait, Earth is not the center of the universe. sorry, Earth. It was a good humility check, right? And so it's a huge change in how we see the world, and parallel to that is where we see this change in how the aurora are started to be reported, starting to be understood. And a lot of that has to do with quite simple things, just communication. The printing press gets invented. People can compare images from place to place suddenly, and we have an increase in population. So just the fact that there are more eyes to see than with, and paralleling with that increased population is that you now have I mean, yes, most of science is done for an upper class, right? But the general population also has as an awakening and an interest in it and an accessibility to it as people are learning to read at various stages. So it opens up the range of who can interpret that beyond just the singular experience. And so that really is the cusp of how all of these things change. And so it's a really, I mean, it's an amazing time in history to be an astronomer. All of these people start sort of popping out of the woodwork. We can look at someone like Johannes Kepler, right? So this is early 1600s, and you're spending a lot of time looking at the stars. You're starting to figure out the motion of the planets, the idea that they're elliptical and the way that they're moving through there, right? People are spending a lot of time watching the skies. We've got Galileo. He's assembling his first telescope in the early 1600s, noting it's not the first telescope, it's just his first, but that's a story for another time. So we kind of pull on these two specifically, and we're going to focus a lot on Galileo in a second, but Kepler is writing about Northern Lights in 1607. Galileo writes about them in 1619. And so I'm picking up the story here, partially because we don't have the time in an hour to cover thousands of years of history. So I kind of picked up at where things start to get bubbling and things start to get interesting. But this is also the time in history when we give the Northern Lights the name that we have for them now. This is when they first start getting called the Aurora Borealis. So this is we're going to borrow a little bit from this paper from George Sisco here. And there's a bit of controversy, although I would argue that George kind of put the controversy to bed, as to who first started calling them the Aurora Borealis. And so when I did that other webinar in November, when I did part 1, even as I combed through a bunch of different references and different articles, it's still, I bet it was 50-50 or 60-40 between Galileo and Gassendi as to who was attributed to it being the original orientator of the name. And we're going to walk through a little bit as to why that is. But I just love this. I think this is so funny. The editor's note when they submitted this paper is from about the 70s, maybe late 60s. Anyways, editor's note. It was suggested that a more appropriate title would be More Than Anyone Would Ever Care to Know About the Origin of Aurora Borealis, but the author objected, which I just think is so funny. Because sometimes that happens. Sometimes we care about something way more than anyone else is going to be caring about it. But we got to paint the picture. We got to understand what is going on in the early 1600s, how this confusion happens, and how the study of aurora sort of develops over the next century. So I just said scientific revolution is kicking off. Things are getting exciting. We've got new instruments. But actually what's happening in parallel to that is that we go through a period where we have very little solar activity. Remember, the sun's not always the same. We think about it as this, constant source of energy, but it has fluxes. It has good days and bad days, or I don't know if that's what the sun calls them. But if we look at it on a really big year here, so this is from the 1100s all the way up to, I think, the 1800s. And then on the graph there, it's just showing you how many observations were recorded per decade. And again, keep in mind, these are southern observations. It's another big thing. People who live with the Northern Lights in the north have a different understanding than what quote unquote science has come to understand it, because they experienced it much different. Same way myths and cultures develop differently, understanding of science develops differently until people eventually start going to the north consistently, or these instruments get taken to the north. Let me say it that way. Okay, so from about 1645 to around 1715, they called it the Maunder minimum. It was a guy who later on identified spirits, so it's named after him. And it's just a period where there's very little solar activity. And so for them, it's just almost 60 odd years of quiet. there's almost very little aurora activity, and so it's a hard time to be studying that or to be interested in it. So that period kind of ends in 1717. There's a really big show that happens, or saying a show, there's a really big showing of Northern Lights. And during that time, the Royal Society of London asked this guy, Edmund Halley, we're going to come back to him a little bit later, to sort of write up about the account. And when he does it, he references that, the first person to call the Aurora Borealis by that name was actually back in 1649 with this guy. He was a mathematician, among a few other things. And so he gets accredited by Halley. And Halley, since Halley wrote the first sort of big summary of the Northern Lights, that what Halley writes gets referenced for the next few hundred years. And this is that one thread where the attribution of who gave it the name gets mixed up. Now, Gassendi himself, he was a peer to Galileo. He actually read some of his stuff back in the 1620s, because when he was writing about it, he was writing about something he'd seen back in 1621. So all of this is just a sort of a bunch of names in history, and hopefully no one is nodding off. But if you are, wake back up, come back. We're going to get interesting, I promise. The reason why I bring this up is that it's less about, for me, it is less about who gets the attribution than it more is about understanding why these things happen. Why is someone forgotten from history? Why are things, sometimes it's accidents. Sometimes a textbook gets left in an attic and no one finds it for 100 years, or a journal, or things like that. But often it is social, and often it is political, and all of these things are always tied together. And so if you scratch at the surface, you learn to be more careful in what you know, because how you know something matters, and who tells you it matters. So what am I saying about that? 1618, there's a bit of a science throwdown happening. So Galileo is on one side, and this other guy named Grassi is there. There was these 3 comets that went through, and essentially Grassi says one thing, Galileo disagrees, but Galileo is in trouble right now, or he's in the doghouse with the church. This should be familiar to maybe some high school science that you haven't thought about in a while. He's in the doghouse because he's pushing forward this heliocentric idea, right? I was saying it before, scientific revolution. The Earth is not the center of the universe. Galileo, even though this idea came out almost 100 years ago, he was starting to champion. He was starting to be like, hey guys, this is what science is telling us. And the church told him very, maybe politely or not so politely, to keep his mouth shut. And so Grassi was Jesuit, and Galileo, because he couldn't openly defy the church at this time, got his understudy and his friend, Guidici, to publish his sort of retribution for this little fight over these 3 comets back then. And so what we're really looking at is that sort of tug of war, right? And those dynamics are interwoven in how we know what we know. And, in this case, it's who named the Aurora Borealis, because it was actually Galileo who called it the Aurora Borealis in 1619, in something that he was written. And then when he gets referenced later, it sort of gets forgotten. And for us, you and I, we know Galileo's name now because of these stories. And so some of that has been retributed and been found out, and other names get forgotten. Not because their science is, sometimes it's because their science is lesser, but often it's just because the way history gets written. Right? So we think about the tug of war of how science gets recorded, or how we know what we know. I mean, one of my favorite science facts to bring up out of this is that, so Galileo ends up dying under house arrest for his belief that the Earth is not the center of the universe, or that the sun is the center of our solar system. And the Vatican, I was going to say, see if you can guess this before you get to the end. Does anyone know in what year the Vatican apologized for arresting Galileo for heresy? Guessing at home? I'll give you a second. 1992. So, I was almost alive, not quite yet. Right, so 300 or so years later, the church apologized for having arrested someone. But that's what I mean. All of those relations are still holding out, still in there. Okay, so science is always political, even if it's not political science. We're getting really bright. Okay, so what was the actual theory that Galileo proposed? So we're gonna get into some of the fun different things of how people started trying to guess what in the world was going on there. So this is a direct quote. I mean, it's translated into English for us, but from Galileo. And I know, academians, that many of you will have seen more than once more than once in the sky at nighttime, illuminated at the north end, parts in such a way that the brightness yields nothing to the brightest dawn, and it rivals the sun. An effect which, in my opinion, has no other origin than that part of a vapor-laden air surrounding the earth is for some reason rarefied, and being sublimated rises above the cone of the earth's shadow, and then is struck by the sun and able to reflect its splendor. So he didn't think it was water, but he thought that some sort of gas was going way, way, way up high out of our atmosphere, or we had a high enough atmosphere that the earth could then come in and reflect on it. And so this is where this sort of stabbed in the dark start off from. And so the next guy who kind of takes a crack at giving a little bit more of a science explanation is René Descartes, which you probably know, or if you do know his name, is more of a philosophy stance, the I think, therefore I am. If I'm capable of doubting my own existence, then I exist, right? That's the nice thing about science back in the day. If you were smart enough to get educated, you could talk about whatever you wanted as long as you could, write up a thing and get it printed. Anyways, we're a little bit more segregated in our disciplines now, for better and or worse. So he kind of riffed off of that, and he was thinking that he thought that it was just ice. He thought that way, way up in the north, as you go to the North Poles, you're getting scattering from sunlight, from the ice particles, and it only happens in really, really cold climates. And so this picture in the background here, this is actually from yesterday morning when I was 3,000 kilometers east of here. I just flew from my home in Saskatchewan, visited my family, back to Vancouver Island here, and weather is very different. It's about -20, so about zero, a little colder than 0 Fahrenheit when I took this photo when I left yesterday morning. Huge, huge sundog happening. And now I'm here and it's probably, I don't know, 60 degrees, 70 degrees outside. Bit of a flip. But what Descartes is pointing out is essentially the science that's the same basis of what a sundog is. Now, he's not right about this. It's not the ice particles reflecting, but this is the basic logic, right? When you get ice particles, and we get this when it's really cold, you don't have to be in the far north, it just has to be really cold, or there has to be a temperature drop with high particles in the high atmosphere, you actually get those big, beautiful rainbows, and it has to do with the degree of ice reflected around the sun. That's what gives us sundogs. Really, really beautiful. So we're getting a couple theories here kicked out in the early 1600s, which is great. But I want to go back to when I was saying that we have that Maunder minimum. So this is caused by sort of a random, prolonged disruption in the sun's ability to kick out solar flares. So that normal 11-year cycle that some people may or may not know about, that gets weakened. And so it gets really quiet. And so this isn't fully understood as to why, but we get that lull, and so we get a lull in science at the same time. But it sort of wakes back up. And I brought up his name before. So Edmund Halley, or at least I know him because of Halley's Comet, right? All of these scientists back in the day, they kind of had a field, but they dabbled. They would try different things. Or really, if you studied the sky, you could study anything up in the sky, right? So we know I'm thinking about comets and things like that. So he obviously studied comets, but he was actually really dying to see an aurora. It was just his unfortunate luck that he was born during this minimum when there was very little activity. So he thought that he would die without ever seeing one. And so even though he'd never seen one, he looked through records and he did his best to try and guess what caused them. So what he thought was that there were these watery vapors which got up, and again, that rarefied thing, so they're getting changed over, their electrons, something gets excited. And then what happens is that there's this, he thought that there was some subterranean fire, and they would get caught, and this sulfurous vapor would get lit on fire and illuminate the atmosphere. This was his theory, which is a bit out there, but I will say it's not unfounded. This is a really cool picture, which there's only a handful of places in the world you can see something like this. This is not the night sky that I'm showing you. This is actually an Indonesian volcano, and it's showing you the electric blue flame of what it looks like when sulfur combusts. And so this is really hot. This is at like 360 degrees Celsius or 680 degrees Fahrenheit. And so it's not that the lava isn't on fire, it's actually the sulfur gas around it is, and it flows and comes out of the volcano. You're able to get these photos. You can only get them at night because there's not enough of a light contrast often in the daytime. This one I think is from an island on Java. And so these craters, it flows out from underneath of the earth. They actually mine sulfur there too, right? So very flammable. So this notion that this sulfurous gas could create light exists at the time. There's a few rare examples of it. So it's not a terrible theory. I think we can, I'll tell you, I'll spoil it and say he didn't get it right, but it was a good try. His second theory, though, I like quite a bit. This one I think is kind of funny. So this was his other theory, which is that the Earth is hollow. So here's what he thought. Supposing the Earth to be concave with a lesser globe included, then in order to make the inner globe habitable, there might not improbably be contained some medium between the balls as to make it a perpetual day. And if such a medium is enclosed within, what should hinder us from supposing that some of this lucid substance, on rare and extraordinary occasions, could translude and penetrate through the shell, and being loose and present in a phenomena above? This seems favored by one circumstance, and that's that it would be thinner at the shells, and that, or the pole, excuse me, the Earth would be thinner at the poles, and then that's where these vapors would escape. Which to you and I now, I mean, if anyone's read Journey to the Center of the Earth with Jules Verne, it's from an era of science fiction where we sort of want this to be real. But again, I mean, this is kind of a weird way to say it, but all science starts as fiction. All science starts as an idea that someone tries to prove or disprove. And so now it seems a bit ridiculous because we're taught in schools and we grew up being told that our Earth is solid and that we have magma and, plates and tectonic plates and things like that. But it was an honest to goodness theory. And while it sounds crazy now, I want to point out that there are lots of crazy things that are real, that are actually real, right? So hydrothermal vents, we didn't discover those until 1977. And this blew, logic out of the water because up until this point, if you wanted to have life, you had to have photosynthesis. And now all of a sudden we had an entirely rewrite a different chapter in the biology textbooks because actually you could have life with chemosynthesis. You could have life without all of these other rules that we developed for our planet. And so even if they sound crazy, or a lot of these theories, looking back on them, sound crazy. They do. You're like, they're right. But at the time, you're piecing together the best of what you know. And I also think it's just a great time to remember that lots of things on planet Earth are wildly wonderful and unbelievable. Sometimes the fact is as magical as the fiction. That's what I always think when I roll through those ones. Okay, but we'll focus with it. We'll focus with Haley here for a minute. So he actually gets to see Northern Lights. He gets to see Aurora. He's so stoked. This is what he wrote that thing for the Royal Society of London. He was 60 years old, and on March 17th, there's a transition out of the Maunder minimum into sort of this new era of Aurora coming back and get solar flares again. They don't know that solar flares yet, though. Remember, I'm sort of letting you in on the secret here. So he gets to see one. He gives up his theories. Once he actually sees one, he abandons the idea that it's a gas underneath, and he starts more thinking about this idea of the old word that they called it was magnetic effluvia. It was this notion of this sort of liquid that was, or this invisible material that was coming from the Earth and following the magnetic lines. And he's getting much closer now, right? So that's what he had. This is his drawing of the concentration of the magnetic lines, coming in around Earth. And if we think about how we actually see Northern Lights today, we're starting to get some of the breadcrumbs, right? This is the shape of the corona. So that's sort of the highest density of aurora activity that we can expect to see when we've got some solar flare action coming in. And when we think about, again, if I kind of go back to what I said before about the colors that you'd see, right? So you're sort of, whether you see it as a flare, whether you see it as just a haze or a curtain or a ring, and then again, that can shift up and down with latitude. And so all this is, we're getting some breadcrumbs. So this March 17th, I'm going to use this as sort of a breaking point. So up until now, aurora have kind of been absent from European skies. And so we're going to walk through maybe the next little while here. We're going to look at a lot of wild theories that people started using to explain the aurora, and we're going to talk about how some of them are a little crazy and how some of them are a little bit right, and most of them are a little bit of both. Okay, so Halley comes up with the idea that there's some sort of unknown magnetic material up in the air that's coming from the Earth. And so, of course, if you have one idea, you got to have many that start floating around. So this fellow, his name is William Durham, and he disagrees with Halley. Although he actually is more in line with Halley's previous idea of something coming from this subterraneous. So he had this idea that volcanoes are actually emitting this vapor, and he thought that aurora were tied to earthquakes, right? So for him, in 1728, he saw aurora before this fatal earthquake happened in Sicily. And he was like, well, 1 + 1 must equal 2. Aurora and earthquakes must be tied together. So he thought that northern lights were actually this great thing because they were used to make peace and safety on the earth by ventilating some of the vapors that were caused these terrible convulsions, aka earthquakes, and releasing some of the pressure. So he thought it was all tied together. So we'll give him partial points for thinking about gases, because he was thinking about the gases that would be emitted. And we find out later that it's the different types of gases that give us different colors. So we'll give him a few points, but definitely a little bit out there. The next big one, and arguably one of the biggest ones, at least sort of as far as how this information got disseminated, was in 1731, 1733, one of those years. Jean-Jacques Dortemere, he wrote the first textbook that was solely focused on northern lights. And he threw out the previous ideas. He said he thinks Halley's magnet fluid is wrong. He thinks that the other guy is wrong. That doesn't have to do with volcanoes. He thinks it's all about the sun. And his explanation is that it has to do with something called zodiacal light, which I've actually never said that out loud until right now. So what he thought was that it's this light that's an extension of the sun's atmosphere. So I will say this is a real thing. If anyone's ever seen, you kind of get like a bit of either depends on the time of year, but you can get it just before sunset or just before sunrise, depending on your hemisphere. There's almost like this sort of glow that precedes the sunrise. And it's not, I mean, obviously there's a sunrise, but it's like farther below. And so it's actually refraction that happens through these particles that are in between us and the sun. And so they can make it so you can actually sort of see light before we get to that turn point in our rotation. So his theory was that there was more of this that was getting sort of bounced back to us up north or at either pole. Actually, sorry, they don't know about the South Pole yet. So we're just talking about the North Pole for now. And so this is what he thought was explaining it. And of course, we might as well just keep throwing out more ideas, right? So same year, another guy, his name is Jean-Antoine Meursault. He's like, no. It doesn't have anything to do with solar light. It doesn't have anything to do with volcanoes or magnets. It has to do with just the air. His theory was that the air at the equator would cause these massive airflows towards the poles, where it would just catch fire and create the aurora. And they he said the air would ferment. So think about something going bad in your fridge and catching on fire. That was his theory. So we'll give him some points. He is right. There are global air circulation currents. They do not catch on fire when they get to the North Pole or the South Pole. But fun to think about all the same, never know. We'll see what comes down the pipe. Sorry, sometimes it's hard to take these seriously as I go through them because I just think they're really funny. Okay, we're going to keep going. We're going to go on to Leonard Euler. So he steps on the scene. He's a really famous mathematician. So we're now up to about 1746. So we're about 10 or 12 years past that textbook that Marianne wrote. And while he wrote his book on zodiacal light, and it was the first textbook that got passed around a lot, most people didn't agree with it, including Halley. Like no one was like, it got printed and spread around, but no one really, bit the hook. They weren't sold on his theory. And so when Euler steps on the stage, we actually, for anyone who's had to do calculus, you have had to use something that Euler invented. He was the one who did function of x, pi. He's the one who started using that symbol for that. I is the imaginary unit. He did a lot of our mathematical notation. So if you don't like calculus, you can blame Euler. He was the reason you had to work so hard to learn all those other symbols. Anyways, he disagrees with Marion, and he puts forth this idea that it's the Earth's atmosphere. And this one's kind of hard to explain, but what he thinks is that they end up like ascending really, really high, thousands of miles, and then light hits them. So he's kind of half on the same page. But I was thinking about it as like a lava lamp, where that it gets sent up, and he was saying that it would stay concentrated at the poles rather than dispersing. So it seems a bit wishy-washy, but the reason why I like bringing up Euler is because you can start seeing there's nothing like some good gossip. There's nothing better than a few centuries-old gossip of people getting their feelings hurt, or back and forth of egos. So this was Marianne's response to Euler in 1747. Notice, if you please, that this is the only occasion upon which Euler has expressly attacked me. I, who never pronounced or wrote his name except to sing his praises. I resent both the honor and consequences of them, and I really wish he would just leave me in peace. And you're like, buddy, you wrote a scientific theory that someone disagreed with. But again, like, remember, same thing is kind of true now, but there's these schools of thought, like whoever you sort of trained under, then they kind of have these bickering schools of thought back and forth. And so they take things much more personal, which is, again, science isn't personal. Trust me, people have been taking science personal the whole time. And then the other one was, there was another guy who came on later, Morton Briggs, and he's commenting on all three of them, Haley, Marin, and Euler. He's like, if they had flaws, it was not so much that their science, it was their egos. Marin was too much verbose and extraordinarily tiresome in his claims to have determined the cause of the aurora. While Euler and Haley were more sensible, it seems clear that each thought he was right. So none of them really gave way. But of course, if you have an idea to defend, there's always someone who wants to come and knock it down. So again, we're going to keep rolling through science. And I said, we're getting a lot of cool gadgets, right? We're in that era where all this stuff is getting invented. And electricity, we're starting to mess around with electricity. So this is a photo of Pontoppidan, I think is how you say his name. He was a bishop from Norway. And he also disagreed with all of those previous gentlemen, but he had the luxury of getting a chance to look at a lot of different electrical experiments. So I don't know if anyone had those toys as a kid where you have the glass ball, and then if you touch it, the electricity goes to you. So his theory was that this generated static electricity is what was causing aurora up north. Which, again, it's a good try. We'll give him some partial marks for the idea of, there's some overlap there. What he was most accurate about, though, was that realizing that it wasn't that aurora were due north, it was aurora were more to the northwest. And so this is the first kind of inkling that it's not about geographic north, it's about geomagnetic north. So that's what we're going to give him some partial points for. Now, these electrical experiments were really cool back in the day. This is, I'm hoping it can move for you guys. If not, it's still a cool picture. This is a display that's set up in the Exploratorium. It's a science museum in San Francisco. And so this is showing you a discharge tube. And essentially, it's where you have a glass tube and the gases are able to conduct electricity and produce light at a very low pressure, but under high voltage. And so once people could just suddenly mess around with these glass tubes, they're like, oh my God, this has got to be what's causing the northern lights. It's got to have to do with electricity passing through the gas like this. We've got it. We finally figured it out. And so, or I shouldn't say we finally figured it out. This is their biggest piece of evidence that they kept sort of coming back to from the late 1750s all the way to the 1850s. They're like, somehow the puzzle, this has got to be part of the puzzle, right? So, okay. So we've got in the background, we've got electricity, but we've still got some other people that are working on different angles and sort of tying more of it together. And sometimes it's even just reaffirming past things that people did 100 years ago and be like, okay, yeah, we still think that's right. Let's keep going. So this one, this was, we can thank Anders Celsius, and yes, it's the same Celsius who we use the temperature named after, who was up in Sweden. 1741, he's making the connection between aurora and magnetic disturbances. So we generally credit him with this discovery. However, there's notes from one of his students which are a bit counter to that, which I kind of find quite funny. So this was his student, Hjorter, and this was who wrote, "Who could have thought that the Northern Lights would have a connection and a sympathy with a magnet? The first time I saw an aurora to the south and noted simultaneously a great movement in the magnetic needle was on March 1st, 1741, in the evening. When I announced this to Professor Celsius, he said that he had noted such a disturbance in the needle to similar circumstances, but had not wished to mention it in order to see whether I, too, would light on the same speculation." I don't know how many times you guys have had, it's like, of course, we're just waiting for you to figure it out, and wondering in the back of your head, did you really figure it out on your own, or did you just wait and it clued in when I told you? But we'll never know to really be able to ask either of them. Okay, so we're starting to suss out that magnetism is important. People are getting a little bit more clever. People are trying to figure out, how close are the Northern Lights to me? So until the 1700s, people believed that Northern Lights were really close to the Earth. Like, they thought that they'd be able to reach out and touch them, or they were just a few hundred feet away. Because sometimes when you get a really brilliant display, it does feel exceptionally close, right? If you go back to the Romans, if you go back to that 1938 newspaper clipping where they thought that the town was on fire, because it looks, it's kind of an optical illusion that way. And so the way they figured it out wasn't actually, it was some basic trigonometry. It was having different observers, being able to get an angle to agree to it. And then if you knew the distance between the observers, you could calculate how far away an object was. The first guy to kind of take a crack at this was Henry Cavendish, who was more famous for figuring out the density of the Earth. He also discovered hydrogen, the composition of water, right? He just did this off the side of his desk. He's like, sure, let's figure out how far away the aurora are. So when he took a stab at this, he got pretty close to guess between about 50 and 70 miles, which is not a bad guess, in fairness. The problem at the time, so remember, this is before photos. They have to draw everything that they see. So it's not that the science wasn't sound. They knew how to triangulate. The hard part was, how did they know that both people were looking at the exact same spot on the aurora? It's a hard, even now it's a hard thing to do, right? And so that was kind of their hiccup. So I'll give you a bit of a prelude. It's not until photography that we really can get narrowed in on the exact height. And that's when it's generally around that 100 and 120 kilometer mark is where we find most of them. They can go down to as low about 90, so just under maybe 50, around 50 miles, and then they can go as high as 250, which would be about 120, maybe like 100, or sorry, it would be, yeah, but maybe like 140 miles, give or take a little bit up in the air. It's kind of a broader range, but generally we're seeing them around that 100-kilometer or 60-mile mark. So I always think it's fun looking at the old tools and things we used to tinker with. So the way they used to be able to measure this was with something called theodolite. I got that right. That's picture on the left is one of the old ones, picture on the right, kind of a diagram. But what you may not have realized is that most of us have actually seen this piece of equipment. You just didn't realize that's what we were looking at. Anytime you drive by the construction people or someone who's doing, some engineering, and you can see them measuring and figure out the distances, that's what they're using. They've become digital, sure, and a lot of the calculations get done for us, but it's the exact same science that's relying on angles and distances of what we already know in order to calculate that. So it's cool when tools last through the era. You kind of know they were a good one. Okay. Okay, so we're moving through time. We've caught ourselves up to the late 1700s, and we've caught up to John Dalton. Now again, he's kind of bringing back this idea of magnetism. People are like, all right, we've got this. It's got to have something in the air, and what they think is that there's some sort of like invisible iron. Right. So when we think about a magnet now, it's really easy with iron filing shavings. And that was kind of logic they base it off of. It's like, there's got to be a connection to that. And so somehow there's this iron that's magically in the air. That's the only way. And they called it ferrofluids. And so they would visualize it this way. And so we're getting closer. Some people are kind of thinking the same thing along the same time, but every 20 or 30 years, there's always someone who shows up and says, no, it's just the aurora reflecting off the clouds. So this is what I kind of love, is that if you look at the few hundred years as the development goes, this was a guy by the name of Monge. So he was like, no, you guys are all wrong. It has nothing to do with magnets. It all has to do with lights and clouds. And so this is one of the reasons why it's hard to push an idea forward. Imagine always sort of building up a few pieces, but then having the same old idea just come back like a song stuck in your head every 2 decades. It's hard to push things through. And so over this kind of time period that we've talked about so far, throughout the 1700s, what has been used to explain the aurora? Everything from weather, clouds, thunderstorms, temperature gradients, earthquakes, volcanoes, moon phases, shooting stars, meteors, magnetism, atmospheric electricity, sunspots. Some people are smart enough. There's a few ideas that pop in there. Zodiacal light, astronomical cycles, right? So it's confusing. It's hard. It's really hard to start pinpointing. But when we switch from the 1700s into the 1800s, we also switch what's going on in the world. So once we step into the 1700s, yes, we're still advancing technology, but a big difference is that there's a huge push in geographic exploration, especially the north, with things like search for the Northwest Passage. So these extensive journeys up into the Arctic are paired with all the scientific equipment that gets lugged with them on these multi-purpose voyages. So as far as we can tell, Captain John Franklin, who, if you haven't heard of him, he's infamous or famous for the voyage that lost essentially 130 men, dies. Most remains are never found of all these men, so we don't know. But it's a tale unto itself. Actually, I think Anthony, one of the other guys, did a whole webinar on it. So if you want to go dig into it, but lots of great books written about it. Happy to dig into another time. So but what's interesting is that he was the first one who was credited with realizing that as you go further north, the aurora get brighter and there's more often. And then if you keep going further north, there's less of them, right? So were I to venture opinion as to the probable situation, I should say that between the latitudes of 64 and 65 degrees north have the greatest auroral frequency, right? So he's kind of the first one to affirm what some other people have been thinking but hadn't been able to fully say. So he's out there in the mid 1800s, and then by the time we get to 1881, we get this fun guy, Hermann Fritz, and he's the one who starts mapping what we call isochasms. So it's essentially the line where the frequency that we expect that we expect aurora to occur. How are we doing on time? So this is just a kind of a cleaner map of what you're looking at before, but you can see the percentage. Those numbers that you're looking at are, as you go further north of latitude, the percentage that you would expect to see the aurora. So again, that kind of mid-latitude, you can actually see it lines up right with Churchill right there. That sort of 100% frequency, if they're there, you're going to see them. It's tucked in right along Hudson's Bay and sort of loops around some of those other places I was talking about. But as you go to the high Arctic, it starts to get lower again. It's not impossible, but it does get lower. So, right. And this is happening on both ends of the world. And it's Fritz actually who's one of the first to provide that evidence. They're like, hey guys, this is happening in both places. It takes a little while for it happens at the same time. We need some more advanced gear for that. But they start to realize that both poles are having this going. All right, I'm trying to keep us going here so I can get to the punchline. So, all right, 1850s. I want to bring up this guy. His name is Olmsted. He's a professor at Yale. And he is one of the guys who really starts pushing for the notion that he's like, hey, everyone, I don't think this is magnetic, what was it? Magnetic effluvia. Effluvia? Oh my gosh, I can't talk. He doesn't think it's magical iron coming from the earth. He's like, I think this is cosmic. He's like, I think this is coming from outside of our planet. And his argument was that just the extent of how big the aurora is, that the velocity was way too fast to be terrestrial. He still wasn't sure what the material was, but he kind of had a bit of clout because he was really famous for meteorites. There was a really huge meteor shower that people call the night the stars fell. It was in 1833, and it was from that time that he sort of gave birth to this idea of meteor science, and that these things are not in our atmosphere but outside of it. So he kind of has that to back him up. He's sort of proven it with meteors, or with comets, or sorry, with meteors. And so he actually passes away. He kicks out this theory in 1856, just before he dies, that this is something to do with the sun, and it comes from outside of our Earth, and it's this cosmic clock that happens. He's like, it's all tied together. And again, we're sort of seeing the threads of the people that have come before him. He sort of agrees with Euler that there's sort of something that's coming from the sun and the light, and that there's some sort of exhalation from the sun. That's like they're on this thought. So he dies in May of 1856, and it's a bit of a kicker because 1859. And then in September 1st of 1859 is when we have what we now call the Carrington event. It is a massive, massive solar storm, which then causes one of the biggest aurora that's ever recorded. So it's so intense that in different places around the world, like communication gets cut off, telegraphs catch on fire. There's so much energy coming in. So what we know now that happened was essentially the sun had what's called a coronal mass ejection. So it's almost like it's like having a hiccup and having this huge amount of plasma and energy come flying from the sun at the Earth. Normally, and this was like, I'm gonna keep calling it a hiccup. It was such a big hiccup. Normally those take a few days to reach us. This one was coming so hot, so fast that it got here in about 18 hours. Which it traveled 90 million miles or 150 kilometers. So it was flying. And so Carrington is there, and he is sort of watching. Well, what he's actually looking at is he is there. The reason why we're able to finally make this connection between, oh my gosh, solar flares in the sun and aurora is that he was there drawing and mapping solar flares. So when he was doing this, he is he's an amateur sky watcher. So there's him and this other guy. See if I can find the other guy's name. He'll come back to me. He's in London and he's sketching these fun, and it actually he's projecting it onto a wall. And so when he's doing this, this crazy flare comes, and I just like this newspaper article before I move on. I kind of did this out of order, but that's okay. So the flare comes at the same time, and all around the world, some telegraphs stop working and some light on fire. There's some that are in Boston where, if you look at how it's set up, they are unplugged from their battery, but they started typing on their own because they got all this energy from the storm. And so he just so happened to be there when this huge energy surge comes, and he is recording on the wall. He's actually sketching out what he sees. So this is how they used to do it. They project what they would see of the sun on the wall and then start drawing the solar flares in around it. So this is an example from someone more present, but you can see a picture of Richard Carrington in the bottom there. So this is from him the day of. He's like, within the area in the Great North Group, there were two batches of intense ray of light that had penetrated a hole in the screen attached to the object glass. I was unprepared to witness it from a very I was an unprepared witness to a very different affair. I thereupon noted down the time with the chronometer, and seeing the outburst to be very rapidly on the increase, and being somewhat flurried by the surprise, I hastened to call someone to witness the exhibition with me, and on returning within 60 seconds, was mortified that it was already much changed and enfeebled. So he was so excited to show someone, and then it was gone by the time he got back. So it was a little bit heartbreaking, but he did get a sketch of it. And there was Hodgson. Hodgson was the other guy in the UK who saw it. So it wasn't just he was the only one. And this is this huge breaking point with how we kind of come to understand Northern Lights, because we get this huge solar flare, knocks out all these telegrams, and then we get this huge cascading effect of the aurora, which is the first time we're able to tie those two things together. Now, Carrington is an amateur scientist, but he actually pushes the idea forward, or pushes the theory forward, and it takes a while to get traction because evidence needs to build up, things like that. But it's this first notion that, we're getting these surges from the sun, and those have rippling effects on our Earth in all these different ways, right? And it gets really exciting. So just checking my time here. I realize I'm a little bit over. My apologies. So I'll wrap up. I played a bit of a trick on everyone until I got excited here at the end, trying to get to it. I spent the entire time talking about everything that the Northern Lights are not what they are. We talked a little bit of how they actually work in solar flares, and I promise I'm going to do a part 3, and I'm actually going to walk through the science, the incredible science of how these work and how they affect our world, and do they make sounds, and how the colors work, and how do I see them, and what's it like to see them in Churchill. But I wanted to walk through, to the best of my ability in an hour, hundreds of years and hundreds of lives that have spent, trying to figure out this amazing phenomena. And some of it is by chance, and some of it is very clever connections, and some of it is just really comes down to being the one who spends the time to pay attention, right? It's the guy who was drawing the sunspot that realizes the solar flare. It's Kepler and Galileo who are looking at planets that start to realize what Aurora Borealis are. All of these things, they all end up taking a huge amount of time. And for you and I, now when you go to study Northern Lights, you see a diagram like this, and you can already start to piece together that. But appreciating how much time and effort it took to get to this complex thought is a hard thing to do. So hopefully that was an entertaining wander through history and through Northern Lights. And if there's any time I haven't taken any questions, apologies for going over. Otherwise, I'm happy to keep rolling into them in part 3 at the end of the month. I'll pass it back to you, Rob.
Thanks, Kristina. So if there are any questions, we could take a few real quick. Just put them in the question field in your control panel. Who was the scientist poet that you were reading from?
Oh, Robert H. I'm going to say Ether, Eather. He wrote The Majestic Lights or The Magnificent Lights, which is where some of the quotes for this came from. Yeah, he's a good one to follow if you're curious. And the book is great. Like, the book is fantastic.
Great, thank you. And were you talking about Frederick Olmsted, the park designer?
I don't know if it's the same Olmsted. Sorry, actually, I do know it's the same Olmsted. So I looked up. It's Denison Olmsted, different Olmsted. But yes, I had to double check that too. There's a few who have the same names as in the past. Yeah, no, this one was it's D Olmsted, different guy.
Gotcha. Thank you so much. We just have a lot of thank yous for this for the webinar. Everyone is really enjoying it, and they're looking forward to the next part for part 3, so we can learn what it is. So I think that's all the questions that we're gonna have. So I'm gonna throw it back to you for some closing comments.
Thank you, everyone, for being curious and having that wonder, regardless of however old we may get. I think that's what the Northern Lights are about. The Northern Lights are about wonder. And I kind of love that even if we, kind of what the poem said at the beginning, no matter how we come to understand them, it's still ultimately about the wonder that we feel for them. So with that, I'll be back. Well, actually, I'll be back with Rob on January 7th for more of an interview guiding webinar, but I'll be back to finish off Aurora January 19th. And then I'm off to Aurora season to guide January 23rd. So if anyone wants to come hang out in the cold with me in February, please do. We still got a few spots up there, but it's going to be a good season. So thank you, everyone. I'll pass back to you, Rob.
Thank you, Kristina. So if you are interested in traveling to see the Northern Lights with NatHab, please give us a call at 800-543-8917, or you can send us an email at info@nathab.com. Our adventure specialists are happy to help you out. Join us tomorrow for our next Daily Dose of Nature, where you can check out this week's lineup, including registration links, on our website at nathab.com/webinars. We did record today's presentation, and the replay will be available on our website soon. With that, I will conclude today's webinar. Goodbye, everybody. We'll see you next time.